But the meat was over. In case. Everybody here?
Yeah.
Yeah. No worries. But anyway, what I want to show you is actually where the actual thinking behind the integral comes from, and then somebody smarter than me sat around, Newton or whoever, and came up with a system of rules to be able to integrate, to go back from the derivative and allow us to do it much more quickly. But here's what the integral really is. Okay, now we're going to start with and I'm going to give you a cool little visual. I got this little program. It's somewhat antiquated, but it actually gives you a pretty great visual of this. I'm going to actually show you a Riemann sum, and I am going to start changing the Riemann sum from like 4 rectangle. And we're going to do a right-handed Riemann sum, although you could do this with anything. But we're going to do a 4, and it's going to go from 4 to 5 to 6 or whatever. And I want you to see how this, where is it? And I had it all pulled up. Oh, well, looks like I'm starting over. Where's that at? Okay, there it is. Okay, so here's just a random function I picked. I mean, I can change the function, but this is a random function that I'm using. And you can see that there are 4 right-hand rectangles, right? And I'm going to be summing from -2 to 1. So I'm basically finding the integral from -2 to 1. I'm a little off at my -2 and my 1, but it's close enough for our purposes. So there, the base is approximately 1 at this point. But as I start increasing the number of rectangles, you'll start seeing that the bases are going to do what?
You're going to get smaller.
The bases are going to get smaller, right? So as I have smaller bases, my guess is, and you're going to see this, I'll tell you what, let's just look at
Where
it.
do you find these programs?
This one, it's been around for a zillion years. At least 25 years. Some lady made it. Some teacher crunched this out 25 years ago and started selling it for like $120 a pop. Surely she's retired. I mean, nowadays there's probably better stuff, but I still like this. And it's already paid for. So check this out. I'm going to start increasing my number of bases, and I am just going to do that by 1s. And you can see that the lost area, the stuff that I'm under approximating or over approximating, is starting to shrink and shrink and shrink and shrink and shrink. And I know this is fascinating, and you can go all the way up through 80 on this little program, but look at the difference there. These little missed values here are over approximated, are getting smaller and smaller. Let's get this over with. And you can see as I'm increasing all the way 54, 64, 74, you can see that I can almost make this perfect, where there's hardly any missed or hardly any over approximated areas there. And the true area becomes more and more accurate. So the integral becomes more and more accurate. Now, I've only had 74 bases. What if I had 1,000 bases, or 1,000,000 bases, or 1,000,000,000,000 bases, or 1,000,000,000 bases, right? Or what if I could go to infinity? Because I know I can't plug infinity in, but I can approach infinity. So if I could think about this as the sum, which is a sigma notation problem, the sum of an infinite number of rectangles where the bases are approaching infinity, which essentially means the number of rectangles, where the bases are approaching 0, or the number of rectangles is approaching infinity, I can treat it like a limit problem as well, and I can get to what an actual integral means. And there are ways to actually calculate these sigma notation problems with really high values. We are not going to do that. And if you're wondering why we even need to see this, AP sometimes, occasionally, usually at least once, maybe twice on a test, they will give you this expression and they'll say, what does it mean? And you have 2 options. You can either actually evaluate that expression with math that you'll never learn, or you can look at this expression we're going to talk about and go, wait, that just means it's an integral. So you convert it over to an integral, and then you use your integral rules. Kind of like, I don't know if you remember, but, and we'll go back through this again, but if I give you a big, ugly limit definition with the sine of x plus h minus the sine of x over whatever, if you can look at that limit definition and go, wait, that just means a derivative of sine, it's a whole lot easier to go, well, I already know the derivative of sine, it's cosine, and find that. It's a whole lot easier to recognize a situation, but then convert it and then use a different method. So that's what we're going to go about today, is recognizing how to convert from this ugly expression I'm going to describe to you to actually a simple integral that you would be able to simplify, and vice versa. So let me just set this up. The first thing we're going to do is actually think about these as Riemann sums, okay? And Riemann sums you already know how to do. There are a whole bunch of what times what? Bases times heights. And we found those bases by doing what? How do we find the base that you are going to use on every one? You did like the b minus the a, right? So you did where I'm ending minus where I began. So if I'm going from like 1 to 12, or in this case, -2 to 1, you take that minus that to get the total length, and then you divide it up by the number of rectangles you want, okay? And then you multiply it by height, and how did you find the height? You plugged an x value into a function. So think like that, base, number into a function. Now I want you to visualize this. If you jump to your book on page 101, you're going to start seeing this develop. Now, before we jump into it, make sure you understand what sigma notation is and what its limitations are. Sigma notation does not actually sum stuff for you. It doesn't. It's just a way of writing it. So like, for instance, if I'm going to actually evaluate a sigma notation, a Riemann sum, that's just base height, base height, base height, base height, assuming I'm doing like a right-handed rectangle. But I could shorten that process. Since we're going to have an infinite number of these rectangles, I really don't want to write out an infinite number of them. So I'm going to represent it with the sigma notation. Now remember what sigma notation does. If you have a sigma notation, again, it doesn't actually do the adding for you, but it means the sum of. That's all it means. Big sigma, the sum of all of these expressions where I ranges from what to what?
2 to 7.
2 to 7. So it basically means plug the 2 in, then plug the 3 in, and plug the 4 in, and keep plugging in until you get to 7, then plug the 7 in, and then the sigma part means add all of these together. That's all it means, okay? So what we're going to be doing is summing, though, a bunch of bases and heights. Now, a couple things I pointed out here. Remember, I is used in calculus this way, not to represent an imaginary number. I think when you guys use sigma notation, and when I did in my pre-cal and my algebra 2 classes, I was always using n. But I is used, j is used, k is used, whatever. So don't be disturbed by seeing an I in there. It doesn't mean imaginary. If you see an I there, that means all of the values from 2 to 7, whole number values, I'm going to be plugging in there. Okay? Okay, so that's the first thing. And then we talk about the 7 is where I end. And again, sigma isn't going to do the adding for you. I don't go, oh, wait, sigma, I know the answer. There's no little trick for that. We would actually have to go and add all this stuff together. But it's a way to show this summation cleanly. And that's what our goal is for in this talk today. Also, blah, 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 constants. If there is a constant that's not, if there's any variable that's not I, or if there's a constant, you're allowed to just pull them out to the front. You don't have to, but you could if you wanted. So like if I'm summing this, 4 is a constant. If I wanted, I could just pull the 4 out front. If the 4 is out front, I could push it back. And then any variable that's not I, like b minus a over n. If that b minus a over n is in there and the variable doesn't match that I, that is considered a constant as well. And that could be pulled left right there or pulled out front. So those are kind of just some of the rules for sigma notation. Should you see something out front, don't freak out about that. It's the same thing as if it was on the inside. Okay, so with that being said, let's talk about what we're actually going to be doing here. And I'm going to use this as an example. And I'm going to walk you through. So if you have at any point, if you're like, whoa, 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 you're going too fast, please slow me down and ask a question. But I'm walking you through why we're going to have some of this funny notation. Okay? Now, if you look at this, again, Riemann sums, I am summing a bunch of bases and heights. So you're going to have a bunch of base expressions, and you're going to have a bunch of f of something expressions. except it's likely that that something that you're plugging into the f will actually be plugged into the function. You'll see that in a second. But initially, you're going to have a bunch of bases and a bunch of heights. And I want to talk to you about what those values are and why they are what they are. So let's start with something really basic like a 4 rectangle Riemann sum, and we're doing a right-handed one. Okay? So if I want to write this, clearly I'm summing the area from 1 to 5, right? So if I was doing something, I'm thinking, okay, I want to go from 1 to 5 on this actual integral, and I'm integrating this right here, okay? But I want to actually think about how would I have found my base if I'm going from 1 to 5? My base would have been what? 5 minus 1 over 4. So I would have had a 5 minus 1 over 4 base. So my base is 1. Now, in your problem, every sigma notation is going to have that base value. So every one, each of these things that I'm summing is going to have a base in there, so you can see the 1 gets thrown right in there. But the way I would have expressed it is 5 minus 1 over n. Now, I also need a bunch of heights. Now, how do I find the height? On this one, which height did I use? First, the height at what? At 2. How did you come up with 2? Why not 7? Why not 4? Use your brain and think for a second. How did I come up with 2? One base length to the right of where I started, which was this. So, and then I plugged it into the function to find the height, right? Well, think about that expression. I'm starting with the a, which is the 1, and I'm adding 1 base length, right? Because I is ranging from 1 to 4. So I'm going to add 1 base length to this, and it's going to get plugged into the function, and that will be my height. Now, for the second rectangle, what base length did I use? Still 1, right? So same base, still 1. But then what did I plug into my function? 3. Where did I get 3? I added what? Another base length, or you could say, well, I've added 2 base lengths to the 1. Well, that's what the sigma does. The first time it plugs a 1 in, so it adds 1 base length. The next time the sigma plugs a 2 in, so it adds 2 base lengths, and then into the function. The next one, a 3, because you're going to eventually add 1, 2, 3 base lengths, and then plug it into the function. And then finally, you're going to finish up with 4, 1, 2, 3, and you're going to plug up 4 additional base lengths into the function. But all the while, I'm using the same base. Are you seeing this? Yes, no? So that's what the sigma notation is doing. It's saying, hey, I'm taking the base times all of these individual heights, and I'm going to sum them together where I goes from 1 to 4. And why does it go from 1 to 4? Because we had 4 rectangles. If I had 10 rectangles, I'd go from 1 to 10, right? So you can see that 4 right there. Yeah.
Because you're allowed to move constants out, should we just move the b minus a over n left?
This one?
I mean, in any of them.
I can't move that one to the left because it's inside this function.
No, just that first one.
But that first one, I totally can if I want to. And AP sometimes will pull it out, sometimes they won't. But does that make sense? And by the way, the 1's not even doing anything. I really technically didn't even have to write it, but it is there, right? Now, at this point, to actually do the math, if we were going to do the math completely, I need to actually plug that right there into the function. Well, what's the function? Are you seeing this? So I take the 1 plus 1i, and I shove it in there, and I write down that function. So what I see right here is a sum of all of the 4 base height rectangles where that's the base and these are the heights. So if I plug a 1 in there, I get the first height. If I plug a 2 in there, I get the second height. If I plug a 3 in there, I get the third height. If I plug a 4 in there, I get the fourth height. And I take all those base heights and sum them together, and I would get my Riemann sum. Are you with me so far? And the only thing that would change is if I don't want 4, if I start thinking, well, I would rather have 5 or 10 or 20 or 30 rectangles, well, then this stuff right here changes. Okay? Like right here, this is b minus a over 4 because I have 4 rectangles, and this would be a 4. If I had 10, I would put a 10 there, and a 10 there, and a 10 there. And I'm going to keep doing that the more and more rectangles I want. Are you seeing this?
What does the A represent in the height?
A, B. Right? So the A is where I begin. Now, if I wanted to do a left-handed Riemann sum, what would I do? I'd actually not want to plug in 2. I'd want to plug in 1, right? Are you with me on that? So I would either do one of two things. One, I would either go, well, I just want to start with A. So if I start with A, do I really want to add a base to it? No. So what would I make I range from? 0 to 3, right? But we're always going to do a right-handed Riemann sum, so don't worry about it. And does it really matter whether I do a right hand or a left hand if eventually my bases are going to shrink so tiny they're thinner than a sheet of paper? It doesn't really matter because they're going to shrink to the point where they're lined up in there so perfectly and so compactly that I'm not missing any area. This program right here, but here's the idea on this. So if this right here is representing my Riemann sum, and again, this would be the sum of the 10 rectangles. That's the base, right? That's the ending minus beginning x value divided up by 10, and then I'm beginning not with A, but one base to the right of A. I plug that into my function. And then 2 bases to the right of A, I plug that in, and I would go. But you can see 10, 10, 10. If I went to 100 rectangles, 100, 100, 100. If I go to 1,000 or 10,000, 10,000, 10,000, 10,000. And what is happening as I get more and more rectangles?
Closer and closer.
My base becomes what? Closer and closer and closer to 0. Now, in a perfect world, I wouldn't have to pull out a limit. I could say, well, why don't we just put an infinity in there? And we'll let that represent the integral. Because if I get an infinite number of rectangles, you can clearly see my base is really approaching 0 now, right? Super skinny base, zillions of heights, right? Because you're literally going to add, tons of these I values, because I is going from 1 to infinity. You're going to add an infinite number of those until you eventually hit infinity, right? You would have all those things squeezed in there and you get a perfect area. But I can't write infinity like that because I can't actually get there. But I can approach it, right? And how do I approach infinity with calculus? A limit. So I leave n in there instead, and I tack on a limit, and I say my n is going to what? Approach infinity. That is your real definition of an integral. That. And it's terrible. But we actually have math to evaluate that stuff. I don't know if you, and I think I mentioned this yesterday, do you remember, I'm going to jump back right here. I think I wrote it in here somewhere. I have it. Oh, yeah. For those of you that were in my class, do these things ring a bell?
Yeah.
They make you a little nauseous?
Yeah.
Mind you, some fun summer reading. These are formulas you would use to do the sigma of a 4th power, 3rd power, squared power. And there's all kinds of sigma rules for sines and cosines that we could learn if we wanted to make this about algebra. But guys, remember, this process I'm showing you is a way to find a definite integral, not an approximated integral. And if I want to find a definite value, a perfect value, I don't have to do this ugly limit sigma notation expression anymore. I can just pull up my integral rules that we already know or should know or know at some level. Okay? Again, what I want you to be able to do is be able to write it in this form. Write that definite integral in this form, and then call it a day. Because they may ask you, they may give you this, and they say, this is called a Riemann integral, what's the exact word? A Riemann sum, basically, a perfect Riemann sum that would actually evaluate this. If they ask you to do it, I want you to be able to know how. But if they give you this on a test and say, evaluate this expression, I don't want you to actually use the math to do this. I want you to convert this back to the integral and just integrate it with the rules you have. Are you with me? Okay, so let's talk about really what's going on. And sometimes the best way to see this is through some examples. So let me just walk you through this one, and then we'll do a bunch of these. We'll call it a day. All right? And then tomorrow we'll really get into fundamental theorem. Okay, so the question was, write the definite integral as the limit of a Riemann sum as n approaches infinity. So we're doing an infinite Riemann sum, basically. Now again, what does Riemann sum do? It adds up a bunch of what? Bases and heights. Adds up a bunch of rectangles, which are a bunch of bases and heights. So what I'm going to start with is like, okay, I'm going from 3 to 10. So how would I find my base? 10 minus 3 over infinity, but I can't put infinity, so I'm going to use n, because remember, I'm going to make the limit as n goes to infinity. So there's my base, 10 minus 3 over n, and I'll put that in parentheses, n. Could you pull that out to the outside? Everybody with me? Stay with me. 10 minus 3 over n. I'm just going to leave it in there for now. That's my base. Okay? And I'm going to be summing all of the bases where I goes from 1. There's going to be an infinite number of them. So I'm going to put n up there to represent infinity. And then I'm going to write infinity, limit as n goes to infinity on the outside. Rather than putting like 10 there and 10 there, if there were 10 rectangles, or 4, 100, I put n goes to infinity. All right, now I need my heights. So where do I begin? I'm not going to start by plugging a 3 in, right? I don't start at 3 on a right-handed rectangle. I start what? 1 base over. Well, what's my base? 10 minus 3, or 7 over n. So I'm going to start with 3 plus 10 minus 3 over n, but I'm going to tack an I on it, because an I is going to say I'm going to add the base once, and the next time twice, next time 3 times, and then that expression gets shoved into my function. So that simplifies to 3 plus 7 over ni, right? So I take 3 plus 7 over ni, and I didn't even do that here. You can simplify that. And I shove that into my function. So 5 times 3 plus 7 over ni squared minus 3 times 3 plus 7 over ni. Base, height, from I, as I goes from 1 to infinity, but I don't put infinity, you just have all these n's, and then the limit as n goes to the infinity, sums them all together. So this is how you write a limit of a Riemann sum as n approaches infinity. It's an infinite number of them, and that is the same thing as this. Now, what you're going to have to be able to do is go both ways. So what if I give you this? What are some things that you can glean from that? If you're trying to rewrite this as an integral, what are some things that pop out at you that might be really helpful? Because again, you're going to have to know this, this, and this. Say it again. Okay, so if I gave you 10 and 3, I'm really spoon feeding you the 3 and the 10, right? But guess what? It's never going to be 10 and 3. It'll be 7, 7, 7. So what is that telling you? And by the way, the thing that you can lock in on the 7 is it's going to be over the n every time, right?
What we know the 3.
The 3 gives you what on the inside here? The a value. So that gives you this. And then the 7 is the what? The difference between the a and the b. So you can add 7 and get this. And then the only thing left to really pull out of that is what? Yeah, what the function is. So how do you determine that? So you got a base, there's your base times a bunch of junk. So that's going to be kind of the function. But I don't write that whole thing down there, do I? What do I replace the junk with the I with? X. And you're left with 5x squared minus 3x. 5x squared minus 3x. And then don't forget your dx. Are y'all seeing this? If you don't, no worries. You just did one. All right. Look at the classwork / homework. So first thing we're going to do is do a couple of these where we go from a Riemann sum, from an integral to a Riemann sum, and then we'll go back the other way. All right, so let's see what we can do. First one, right here. I want to have the limit. You're always going to have the limit as n approaches infinity, because you want to have an infinite number of sums, right? But then you want the sum, so then you're going to have the sigma notation as I goes from 1 to what? N, which again would be infinity. And then here you're going to have base height. So initially I want base. Now how would I find base? Top minus bottom, which gives me 6, divided by the number of rectangles, which is infinity, but I don't write infinity, I write n. So 6 over n. That's my base. And then initially what I'm going to do is I'm going to take one little step right here and say, all right, what am I plugging into my function? Now, if you're good enough to not have to do this, you don't have to, but I'm just showing you this first step as we get started. So what will I be plugging in my function? Well, I start with -1. No, because if I plug -1 into the function, I'm doing a left-hand Riemann sum. We're going to do right hands. So I don't add -1. I do -1 what? Plus what? 1 base, 6 over n. And then the next one I'm going to do 2 bases, right? Next one, 3 bases. So how do I show that that number of bases is going to be changing? I put the I in there that was represented here. Now that's what gets plugged into my function. So when I plug that expression into my function, what do I end up with?
All of that cubed.
All of that cubed, but the f goes away, right? Are you seeing that? So if I were to take that and plug it into that function, I get times all of that cubed. And there is my limit, which is my infinite Riemann sum. You with me? Let's try it again. Let's jump to number 3. So on number 3, so I'm doing an infinite Riemann sum, right? So I want the limit as your n goes to infinity of the sum of all the expressions, the bases and heights, where the I ranges from 1 to n, which is essentially also infinity. And what is the length of each base? B minus a, which is 5 over n, because I want it at 5 over an infinite number of rectangles. So there's my base. And yes, you could factor that out if you wanted to, but you don't have to. I'm just talking about license here, what you're allowed to do. And then I'm going to plug what into my function? Now, if you want to keep from having to rewrite this whole thing, you might just do that out here. What do I end up plugging into my function? Start at the -1 spot and add what? 1 base, then 2 bases, then 3 bases. So I bases. So I'm going to be plugging -1 plus 5 over ni into the function. Now, what is the function? That. So big parentheses. I'm going to plug it into the squared -4 and plug it in to that. Both those spots. So I'm going to take that and plug it in there and there. And that would represent my function. So -1 plus 5 over ni there. -1 plus 5 over ni there. You tracking?
Tracking.
And just leave that out on the kitchen counter. Your parents will be like, oh my gosh, it's impressive. Look what they're learning. Yay. All right? All right, let's go the other way. So this is totally possible, but what I have seen probably a little more of is you just getting an expression like this and they just say simplify. And you're like, what? Because there's math to do that, but I don't want any part of it. So what I'm going to do, I mean, you literally have to use those formulas, those ones that we learned in math team land that most of you haven't learned, or at least half of you haven't learned. You'd have to pull those out and then take a limit of that expression using your limit rules. It should be awful. I don't want any part of it. Too many ways to make mistakes, and we already know how to integrate. So can I convert this into an integral? So what things pop out at you? We want to rewrite this as an integral so that in the future we'd actually be able to integrate it and get where we need to be. So where am I going to begin? Do what? You can. Yeah, I'm going to hold on to that 4 because it might have something to do with my function. So remember, I might have switched up some terms on you to be a little sketchy. Okay? So you think about it. I see this as what? That's my base. So what I see, if that's my base, then all the rest of this right here, this part right here and that part must be my function. So remember, even though I might switch it up, I don't have to line it all up nice and neatly in order for you. Okay?
So the function is 4x squared.
Looks like it. So you can see that this base plus a value got shoved into a squared value. So you know it's x squared, but that 4 came from somewhere and it's not part of the base. It must be 4x squared. Don't forget a dx. Now, what did I go from? What to what? Began at 1 and went from 1 to what? 6. Why? Because my base, that top number is b minus a, right? And if the top number is b minus a, that means the difference between where I begin and where I end would have to be 5. So if I have to be 5, I'll just add 5 and get 6.
Can you pick any two random numbers?
I'm sorry?
Can you pick any two numbers for that?
No, because the first one has to be 1.
Oh, my bad, yeah.
Is that?
Well, no, it should be -4.
Oh, I have a different key. I hope the key's not.
Because b minus a, 1 minus x equals.
No, 1
A
and
is
A.
1.
A is 1. Yeah, because of our formula. Right? Are y'all with me on this? I'm gonna have to change my key is not this. It's a different problem.
Oh, there was an issue. I don't know.
The one you texted me about?
No, it might have been last week. I don't remember, but
Yeah.
I'll find it.
If you haven't texted me, tell me.
Sam, was it? It might have.
If it is, let me know, because again,
Some of that during.
if I have bad keys, I want to fix those for you.
Oh,
Yeah, yeah.
I'll tell you about it.
Tell me later.
It was
All right.
60-something.
Let's try number 5. Okay, so I look at this, I see a limit of a sigma notation, and I go, oh, must be an integral problem. But man, I don't want to do this, so I'm going to try to find the integral. So finding the integral, what does that -1 tell me?
Starts at negative.
So real quickly, look for the value that has a base times I added to it. That's your a value. So I can quickly get started. Now I only need 3 things: the a value, the b value, and the function.
Function just looks like x cubed.
And the function does end up being an x cubed because here's a base, that's your base, and all that's left is that thing plugged into in cubed. So it must have been plugged into an x cubed function. And then the last thing I get out of this is what? You see your base show up right there, 3 over n, 3 over n. So that means the difference between b and a is 3. So if I began with a -1, I'm going to have to end with a 2, which is 3 away, and then don't forget your dx. You with me? And then now I can integrate easily. I mean, think about it. All I got to do now is go x to the 4th over 4, and then we'll talk about the fundamental theorem tomorrow. I plug in the 2, plug in the -1, and subtract. But we talked briefly about that yesterday. But we'll do a little modified version of it and get into that tomorrow. But it'll be easy, okay? What about number 6? Oh man, it's so ugly. No, it's just meant to make you a little concerned. But let's look at it. Limit sigma, immediately I go, oh, that's an integral. What can I get out of this real quickly? I look at this and say it
So A is e to the fourth.
carefully. What's A?
Oh, wait, no.
4. Because that's what got plugged into the function. You look for the base I, and whatever the base times I is added to, that thing that it's added to is your A value. So I can go, oh, 4. Now, what is the base value here? 3 over n. So what does the 3 tell you? It tells you the B value is going to be 7, or 3 more than 4. And I'm rocking along here. Now, if that right there is the base, and then this is what got plugged into the function, what's your function? E to the 2x. And I can integrate that with the simple U substitution, right?
How'd you get 7 again?
Because the base value, when you look at a number over n, that number over n means b minus a over n.
Which one is B and which one is A?
Well, no, it's the b minus a is 3. That's the a, that's the b. So if I've already figured out the a is 4, then just algebra tells me the b must be 7. I'm basically going to add that. I'm going to add that 3 to that 4. All right? All right, jump to this thing. What do you see here? Well, we could do 7. Have we done 7?
I think A would be better now.
You like this better?
Yeah, we have plenty of time.
Okay, check out this one. We can do them all. Okay, right here. So limit sigma, oh, it must be an integral. Now on this one, you see the base I, the 3 over ni, isn't being added to something. Does the world crack? No, that just means your A was 0. But what is your B? 3 away from 0. And when you eyeball it, there's a regular 3 over n. That must be my base. So this right here is the expression that got plugged into your function. So what's my function? 5x squared minus 2x. 5x squared minus 2x. Don't forget the dx. Tracking?
Yes.
And then jumping up here to number 7. Again, limit sigma up must be an integral. Where am I beginning?
-1.
-1. Where do I end?
6.
Y. 7, 7, 7 is the distance between A and B. So I add 7 to get to make a separation of 7. And then I look back through here and it might still look a little ugly. So I'm going to circle out, okay, that part's the base because it doesn't have an I. And then it looked like this got shoved into the function twice. So what do I end up with? That's my function. 3x squared plus x. 3x squared plus x. Don't forget your dx.
Can we go back and check number 2?
Number what?
Number 2.
So number 2,
And the key is not there.
the key isn't there at all.
No, like the problems are different. And the
Okay,
completely-
well, that won't matter because we've done them all.
Okay.
But I will try to still fix it. Yeah, I can see that there. It's not the same. So right here, I'm saying, all right, if I want to write it as an infinite Riemann sum, I'm going to have the limit as n goes to infinity of the sum of all the bases and heights where I goes from 1 to n. So that's standard. Now I need the base expression. How do I find the base? 7 minus 2 over n, so 5 over n. Right? And then I'm going to have to plug something into the function. What am I going to be plugging into the function? I'm going to write out to the side here. Where do I begin? Not with 2, but with what? 2 plus 5 over n I. So that's what gets plugged into my function. So what do I have here? 3 sine of that. 2 plus 5 over n I. Child's play. And remember, just like that ugly limit expression, at the time we did that limit expression, the f of x plus h minus f of x, I told you guys, hey, let's take a step back, find the function. Now we've got L'Hopital's rule. We don't need to do a lot of the stuff we did back then, because back then we only knew limits. Now we know derivatives. We can do L'Hopital's rule, and that's the approach I will take on those problems moving forward. But this, you've got to have a bridge. You've got to be able to go from here to here or vice versa to be able to get them. And they're not hard. You see it. But you're probably never going to, I'm not going to talk about this again, but it'll start popping up on the practice tests. Popping up on, so you have to remember this, and it will totally, I'm sorry, you'll see it on your test. But it's a very isolated thing, because from here on out, we're going to be learning how to actually integrate these things from 2 to 7 and find the exact value. That'll begin tomorrow.
Let me show you that.
Yes. So more Riemann.
So basically, we got all base here, some base two, and basically you plug in, you get the right result. But on the key, you plug in, I don't know, you have 2 or 5. So that you're plugging in the right light. Should be plugging in the left.
Oh, I plugged 2 in
So it should be.
instead of 12. Okay, yeah. Yeah, thanks. So it's just a one-page thing, right?
Yeah, I think so. It's 99 is off.
Yeah. We're all trying to decide if we're listening.
I don't know why he.
One of your friends get into it recently?
I mean, a lot.
He bought into
Like how many shares?
Not a lot.
Like 5 or?
I mean, I don't really want to like comment on the financial standing of my friends.
I don't even know who they are though.
Oh yeah, about 1,000.
1,000 shares?
No,
$1,000? Oh, okay.
After 5 years,
1,000 shares, that is a lot.
yeah, no, that's a lot.
So $1,000, so he's lost half that.
He's lost a lot more than half that when he got in.
He's a bit in the hole.
Yeah.
I think
I'm telling you, it's gambling, man. That kind
Of
of,
course it is.
yeah.
Gambling is fun sometimes.
It is. If you can afford to lose it. I had a student of mine ask me once, Mr. Hurry, after we had a little stock thing the junior year, he goes, his senior year, he came back, he goes, hey, I just inherited $3,000 from my aunt. He goes, I want to invest. What do you put your stocks in? I was like, I'm not telling you that. I said, because I don't want you to do what I do, and then it goes bad, and you're like, no.
Say this is not financial advice.
Well, for the longest time, I wouldn't tell him. He goes, can you just tell me this? And I'm like, okay, I'll tell you, but I do not endorse any of this. So I had this stock called JDS Uniphase that I had bought at, I think, $30 a share. And I bought, I don't know, 100 shares, maybe. So I bought it 30 bucks a share, 100 shares, and it went from 30 to 150 in 6 months. And I was like, sweet. I'm like, man, we're going to Europe. And I was so excited. In the next 6 months, it went from 150 to 10. Okay? Now, no, because everybody says, oh, why didn't you sell high? High would have been 40. I mean, if you make 10, I mean, yeah, if it goes from 30 to 40, you're like, man, I just killed it. Right? And then it goes to 50 and you're like, oh my gosh. Then it goes to 60 and you're like, you're just giddy. You never know. And it's so hard to sell when it's running. And the whole market as a whole is running. And it's the number 1 fiber optic company in the world. It ran to 150 and then it started dropping. It's still the number 1, still had great information, still had great dividends. All the kind of stuff it was doing was performing, but the market was suffering as a whole. it not only went to 10, but then it went to 2. And then they said, man, at $2 a share, it looks like a penny stock. You know, sometimes I have a stock split.
Yeah.
Stock splits are when the stock gets so outrageously high, they go, hey, we're going to double your shares, but half the price. Doesn't really do anything, but it makes it look like more affordable. Well, this stock looked so crappy, they had a stock merge. They had a 7-to-1 merge. So instead of owning 100 shares at $2 a piece, now I own 14 shares at whatever, 21 a piece or whatever. Then it went to 2 again. At some point, my valuation on my stock was worth less than the cost of trading it and selling it. So I think I wrote it, I finally sold it one day and just wrote off the loss. But my student put all 3,000 in JSU. And he bought it at like 30 or 40, and he too wrote it up to 150, and then lost it all.
Wait, but did it start like when it went
So the
down
best thing
from-
I think you can do is put it in an index fund that represents 500 companies, so you don't get hammered like that. And it's less like
Even if it's pretty zero, I don't think she is. So yeah, no, that's what. No, I think.
Mr. Hurry,
Yeah,
could you fill this out for me? It's for the National Honor Society.
yeah, man, put it right there. I get it.
Thank you. Hey, Mr. Hurry.
See you, man. Have a good one. What's up, guys?
study it. I mean, I can study it before. Yes. Wait, hi. Are you Smith?
Yeah.
Okay, cool. Wait, no.
I didn't have the words, but I still got a 67. I didn't have the list.
Oh my God.
What day is it Saturday? Seriously?
Same.
I was
don't know how to
Sunday too. I was.
It's like that's all I do.
I'm not going. I think I'm not going. We're supposed to add on. Wait, what time does it start?
Okay, I know how to do that one.
Grouping them together.
I know how to do this one because you add them all together and it's like 10A plus 10B plus 10C equals 30, and then you can just divide it all by 3 and or divide it all by 10. I couldn't figure out the other one though. Yeah.
Wait. Are you sure? I can just go back. Is that right? Yeah. What's the lunch for the dance maker or something? No. Wait a minute. I did it. No. I think it's. Yeah, I think. No, I'm not right.
All right, guys, we're looking over these tests, and let me know what you're thinking. If you got a question, if I graded something wrong. I think I stiffed you out of points. Whatever. If you've got a question, tell me which version it is, and I'll throw it up here and we'll take a look.
Use 17 on test B.
Which, is it the test or the quiz?
Just a test.
The test. Okay, so test B, number 17. And everybody has taken both of these, right?
Yes.
Okay. So 17. All right, so anytime I see a square root on this section, I think send me something, but I probably don't know. So I immediately square both sides to make it look a little better. So when I square both sides, I got that statement on the right. A lot of you, when you square both sides, you just forgot to square that, you put a 4. So that hurts you a little bit. But if you square both, you get rid of the radical, make it 16. Then I distribute that in. So when I distribute that in, I get 16 minus 16x squared. That started to look more and more like a conic. I see the two squared things, and I think they probably all need to be on the other side. So I add that 16x squared there. Now it really looks like a conic, but these aren't the same. And if they're not the same, but they're both positive, it must be an ellipse. So ellipses need to be equal to 1. So I divide by 16 and I get my ellipse. So I'm going to have an ellipse at the origin, left and right 1, up and down 4. But it's not an ellipse. That's an ellipse. But I want you to graph that. So I go back and keep what? Just where y is positive. So I keep the up part, top part.
You did 15 on the same test.
Yep. 15 said determine the equations of the asymptotes. So the asymptotes of that, that would mean it's a hyperbola. So what I need is the center. And I have the center there. It's at 9,3. So the center is at 9,3. So I'm going to go x minus 9, y minus 3. I had a bunch of people put squared on that. Remember, these are lines, not parabolas. All right, so you don't want to do that. And now I need the slope. And I'm going to have two slopes, a positive and negative one. So I can go ahead and tack that on there. Now, if I were to be sketching out this graph, this hyperbola, I would be marking off the box, right? I'd be going up a certain amount and left and right a certain amount to get the edges of the box. And the edges, the amounts I move up and over are the slope values that I'm going to use for my actual slopes. So how much did I rise on the box? Well, I rose whatever was being squared into the y, which is 3. And I ran whatever's being squared into the x, which is 3 root 3, or root 27. So I'm going to rise 3, run 3 root 3. I canceled the 3's and I got 1 over root 3, and I rationalized. Stuck that in. But don't memorize A over B. We talked about that because the A is always that one, and A is not always what you're rising. In this case, it ended up being B over A. Could have been A over B, though, if the X's and Y's were switched. But whatever's under the Y is always your rise value squared. Whatever's under the X is always your run value, because that's where the asymptotes come from. They come from the box movements. What else? Anyone?
For the test A, number 19, is it supposed to be y equals?
Test A, yes.
Okay, yeah.
Yeah, and that was a bonus on the one about determine the equations of the directrices. I know it didn't say bonus on it because I forgot to make it a bonus, but it was a bonus. So if you got the determine the equation of the directrices on test A, it was 19. On test B, it was 27. If you got that right, there was test A right there. But you had to go y equals k because the graph was going up and down. So if the graph is stretched this way, it's y. There are y equations. So you did the y equals k and then did the a squared over c. On the other graph, same thing. On the other one, because the parabola is being stretched this way, the directrices are over there. So you had, again, it's crossing the y-axis, so y equals k. You will probably never see that in your life, even if you're take college algebra or something in college. It's just something that shows up at a Vestavia tournament. I think they're the only ones who've ever asked that question. It's not even in textbooks that I've ever seen. I just found it on the internet once and went, I guess it does exist. But they like doing that, sticking it to the common folk. They're the man, I guess. Well, I don't know. They're just stomping on the proletariat, I guess. I don't know. It used to be worse. They used to actually compete in their own tournament, which is so unethical. So they literally learn from a teacher. They learn this certain style and all these kinds of things, and then they compete at their own tournament. Go figure. The only reason why people didn't hate them for it worse than we already do Vestavia is because they were better than everybody back then. They would win the national competition every year. And then when this lady, Kay Tipton, retired, they kind of took a step down a little bit. They're still probably top 5, top 10. But they take a little bit of a step down.
We hate Vestavia.
That's right. Anybody else? Anyone? All right, let me get those back from you. You can just undo them if you folded them back, and I'll just take them up together. That one? Yes.
Oh, my bad. I'll move that.
All right, so new chapter today. And with a new chapter comes a new assignment sheet. All right, so kind of a short chapter, just 6 days of stuff, really 5 days of stuff, and actually really 4 days of stuff. Because Monday, Tuesday of next week, we're just going to practice everything a couple days worth, just to make sure, kind of see some problems at maybe the math team level of how they would ask this. And then we're going to have a test next Wednesday if everything holds and everything's running smoothly. I kind of like this chapter. I think you probably will, as far as liking chapters like it too. What we're going to do today, though, it really has nothing to do with the rest of the chapter. It's in this chapter. It needs to be covered at some point. It's actually a huge deal with AP Calculus. So I want to talk to you about how it might look in AP. Well, I'll tell you what. I'm just going to talk about how it looks here. And then in AP Calculus, I'll talk about why it's a little bit, it seems a little different than here when you get to AP Calculus, because they write it in a different form of that equation. So you might be a little confused in a couple of years when we revisit this, but I doubt it. Most people will be fine. Okay, so what we're going to talk about today is variation. And you probably have, let me turn this up. You probably have heard people say things like, oh man, that's directly related to this. Or yeah, or those things are proportional. You did proportions when you were in geometry, right? When you're dealing with similar triangles. And you compared maybe the hypotenuse over the short leg with the hypotenuse over the short leg of two different similar triangles. Well, those proportions or those variations, that's what we're going to talk about today. And I'm not video. I cannot see. And I'll do that. I cannot see the screen. Okay.